Hello everyone, this is Gregory from ChemCore. This is the polarity and partial charges explainer video where I'm going to be going through the worksheet available in the description below. If you haven't watched the topic video for polarity and partial charges, that is also in the description below. Make sure to go check that out. We're just going to go through every problem as I would do them, and I'm going to explain how I'm doing them along the way. They're asking us to draw the Lewis structure, determine the formal charge of every element, and draw arrows to designate polarity, determine if the molecule is overall nonpolar or polar, and how many nonpolar polar bonds exist in the molecule. I'm not going to be writing what the formal charge of every element is, although it is on the answer key, also in the description below, but we will also be designating partial charges to every element. I'm just going to be verbally saying what the formal charge of every element is. The first problem, NF3, if you're still iffy on drawing Lewis structures, make sure to go check out the video and the worksheets associated with that topic. Nitrogens are going to be in the middle, surrounded by the fluorines. And the nitrogen is going to have a lone pair here, and each fluorine is going to have 3 lone pairs surrounding it. And according to our electronegativity, fluorine is much more electronegative than nitrogen, so we're going to draw these arrows in blue to show that the electron density is going to be surrounded mostly on the fluorines. And since the electron density is mostly around the fluorines are going to be partial negative charge, shown by sigma negative, lowercase sigma. And then the nitrogen is going to be partially positive, right? Because it's losing some of that electron density. Since let's try to see if we can, maybe cancel out some of these polar bonds to see whether this molecule is overall polar or nonpolar. The ones left and right do cancel each other out, but the ones up, there's no other bond that's going down. So this bond going up doesn't really have anything to cancel it out. Therefore, this molecule is overall polar. We're just going to write that out, polar, okay? However, it does have 3 polar bonds and no nonpolar bonds, right? Every bond in this molecule is polar. Did we forget to do anything else? The formal charge, obviously, of every molecule, of every element has exactly what it wants. Therefore, each element has a formal charge of 0. And we'll continue just verbally saying what the formal charge is throughout the examples. SCl4, sulfur is going to be in the middle, surrounded by the chlorines. And sulfur 6, sulfur still has a lone pair over here, and each chlorine will have 3 lone pairs. Make sure to draw that. And as we finish this Lewis structure, we'll notice that each element has exactly what it wants according to our Hunk mnemonic. So all of the formal charges in the structure is 0. And chlorine is a lot more electronegative than sulfur. And so these bonds are going to be, these arrows are going to be pointing near chlorine, toward chlorine, to show that chlorine is going to be stealing some of this electron density away from sulfur. And since it's stealing the electron density, chlorine will be partially negative. Every chlorine will be partially negative, while the sulfur is going to be partially positive because it's losing some of that electron density. And let's try to cancel out some of these bonds. The ones left and right do cancel out, but the ones going diagonally up, left, and right don't really have anything to cancel them out. This lone pair doesn't have any electronegativity on its own. And so this structure will be overall polar. And it does have 4 polar bonds, right? Every bond in this structure is polar, and it does not have any nonpolar bonds. I'm just going to write NP. The next structure, pH3, phosphorus again is going to be in the middle, surrounded by the hydrogens, and hydrogens don't have any lone pairs. But phosphorus 5 tells us that there will be a lone pair on phosphorus. However, phosphorus is way more electronegative than hydrogen. And so these arrows are going to point toward phosphorus, stealing the electron density away from hydrogen, meaning that these hydrogens are going to be partially positive. Notice that, the arrows don't necessarily have to point inside or outside. They can point in any direction, outside, inside, left, right, diagonally. It really matters about the electronegativity. And this phosphorus is going to be partially negative since it's going to have more electron density around it. Now let's check. Every element has exactly what it wants. Phosphorus 5, hydrogen only has one bond, and so the formal charge of every element in this molecule is 0. However, let's try to cancel out some of these bonds. The left and right do cancel out. But the one going down doesn't really have anything to cancel it out. So this molecule is also going to be polar. Once again, it has 3 polar bonds and 0 nonpolar bonds. Excellent. The next problem, CH3Cl. Let's draw a carbon surrounded by the hydrogens and the chlorine, and we'll draw one bond to each of them. And we'll also have chlorine with 3 lone pairs around it. And notice that the carbon-hydrogen bonds are not polar, right? We're not going to have any arrows going from hydrogen or chlorine or to carbon. However, chlorine is a lot more electronegative than carbon. And so we're going to have these arrows pointing toward chlorine. Therefore, once again, every element in this structure has a formal charge of 0. Everything has exactly what it wants. However, the only bond in the structure that is polar is carbon to chlorine. So chlorine is going to have some electron density surrounding it, right? Some negative electron density. We used to do that in blue. Let's keep it blue for consistency. But carbon is going to have some of that loss of electron density. So it's going to be partially positive. And therefore, this structure is still going to be polar, right? We have nothing on the left side canceling out this arrow. But it only has one polar bond, right? And the rest are nonpolar. So it has three nonpolar bonds. The next structure, Br2. Let's just draw these bromines attached to each other. The Lewis structure is going to be. And there is going to be 3 lone pairs around each of the bromines, as usual. And notice that, well, bromine-bromine, this bond is definitely going to be nonpolar. There's nothing else going around in this molecule, so we don't draw arrows anywhere, and there's no partial charge anywhere in this molecule. And just to clarify, there will be 0 formal charge on each of them, right, because they have exactly what they want. So this structure is overall nonpolar. It has 0 polar bonds and 1 nonpolar bond, the only bond in the structure, and it's going to be nonpolar. And the next structure, HNO2, it's a little bit of a trickier, let's keep the same color for consistency. It's going to be a little bit of a trickier Lewis structure, but we did review it in the other videos, this exact structure. So if you don't really understand how we did that, go check those out on my YouTube page. And so we'll make sure that everything has the lone pairs that it wants. Everything has a formal charge of 0. Everything's happy. And there are some polarity going around, right? Oxygen is much more electronegative than hydrogen, so this arrow is going to be pointing toward oxygen. And oxygen is more electronegative than nitrogen for both of these examples. And so these arrows are going to all point toward the oxygens, either one or the other. Therefore, these oxygens, both of them, are going to have a partial negative charge. I know my sigmas look weird, but it doesn't really matter. I think your professor will understand. And the nitrogen will have a partial positive charge as well as the hydrogen. And since these bonds in no way do any of them get canceled out, right? These don't cancel each other out, as well as these don't cancel each other out. And so this molecule would be overall polar. We have 3 bonds in the structure, and all of them are polar bonds, so 3 polar bonds. And 0 nonpolar bonds. Excellent. The next structure, C2H2, is going to be a triple bonded carbon. This becomes important later on. We have a name to the structure, but we don't really have to know it now. Each element in the structure, once again, has a formal charge of 0. Everybody's happy. And carbon-carbon bonds are nonpolar. Carbon-hydrogen bonds are also nonpolar. This is a very important concept. We're going to be seeing this a lot throughout not only this worksheet, but throughout the entirety of this course. Carbon-hydrogen bonds are nonpolar. It's a very important concept to know. And so we're not going to have any arrows pointing in any direction here. Therefore, this molecule is overall polar. Nonpolar. We don't have any polar bonds. And we have 3 nonpolar bonds. The next structure is CH3NH2. We're going to have carbon surrounded by hydrogens. On the left side, connected to nitrogen over here, which is, we should also draw it correctly. We'll have a lone pair next to it. As it's used to, everything has exactly what it wants. Everything has a formal charge of 0. And notice that, again, carbon-hydrogen bonds are nonpolar. But carbon-nitrogen bonds are polar. And so we're going to have a arrow pointing toward nitrogen. Nitrogen-hydrogen bonds are also polar. So these arrows are going to point toward nitrogen. And I see that these two bonds kind of cancel each other out, right? If you push a box against each other, right, and they're both the same strength, they are going to cancel each other out. But there's nothing on the right side to cancel out this bond. And so this structure is overall polar. There is some inequality. However, there's 3 polar bonds, right? 3 arrows that we drew. And the rest, there's also 3 nonpolar bonds. The carbon-hydrogen bonds. We should make this grammatically correct. The next structure is CH2Cl2. We're going to have CCl. I'm going to try to draw it nice and symmetric, right? The hydrogens are crossing the hydrogens, and the chlorines are crossing the chlorines. Make sure that the chlorines have all their lone pairs, and everything's happy. Everything has a formal charge of 0. Carbon-hydrogen bonds, once again, are nonpolar. However, chlorine and carbon are polar. And so these bonds are going to be pointing away from each other. And notice that these two bonds definitely cancel each other out. They're going directly in the opposite direction of each other. And so this structure will be overall nonpolar. All the bonds cancel each other out. Overall nonpolar. However, we do have some polar bonds. It is totally possible, as mentioned in the video, that polar bonds exist. And we're also going to have two nonpolar bonds. Excellent. The next structure, CH3CH2Cl. We're going to take some time to draw this out. Very similar to 2 problems ago, except an extra carbon. We're going to have Cl over there. Cl has its lone pairs, and everything is according to our honk mnemonic. Everything is happy, and the only bond here that is polar is this carbon-hydrogen bond. And so this structure, nothing's canceling out this arrow. The structure is overall polar, with only 1 polar bond, and 1, 2, 3, 4, 5, 6 nonpolar bonds. The next question is a multiple choice question, and it's asking us, which of the following compounds contains polar covalent bonds? Well, a little shortcut that I can do is polar covalent bonds. Let's focus on the covalent first, right? Let's find any structure. If there's any structure that doesn't have covalent bonds, well, we can eliminate that. And the only structure that I see that doesn't have covalent bonds is lithium fluoride. Right? Lithium is a metal, fluorine is non-metal, and so there's going to be a very large electronegativity difference, forming an ionic bond. And so let's think about the rest of these answers. Maybe we can use some shortcuts, some logic, instead of drawing these structures out to maybe determine the answer. S8, well, if you think about it, right, you might be thinking, well, how do I even draw that? It doesn't even matter, right? No matter how you organize this molecule, sulfur bonds, which is the only bonds that are going to be present in this molecule, are definitely nonpolar, right? It's the same molecule twice, and so these bonds are all going to be nonpolar. And if all the bonds are nonpolar, well, this molecule is definitely overall nonpolar, right? But we don't even need to know what the molecule is overall nonpolar. None of these bonds are going to be polar. It's just sulfur bonds. At the same time, same logic, the fluorine-fluorine bond, right? This is a little bit of an easier Lewis structure to draw. But since it's the same molecule bonded to itself, this bond is also going to be nonpolar. And the last structure, I mean, we had some Lewis structures that were very similar to this. Looks kind of like this. Right? Not a very great structure, but you can see that the fluorine is definitely going to be polar with carbon, but the rest are going to be nonpolar. They're not asking us how many. They're asking us in general, which of these compounds contains polar covalent bonds, and the only answer for that is D. Which molecule does not have a dipole moment? We define the dipole moment. If it has a dipole moment, then it needs to be polar, right? A dipole moment only exists in polar molecules. And so the answer must be a nonpolar molecule. Overall, right? Overall nonpolar. And so let's find there's, every single one of these problems has a carbon bonded to fluorine. And so let's see if any of the arrows we can draw in this molecule ends up canceling out. So fluorine is definitely more electronegative than carbon. So let's draw these arrows in every single one of these problems, and we'll analyze right now. So starting from A, these two arrows definitely don't cancel each other out. They're pointing in almost opposite direction, almost the same direction, right? And so they're not going to cancel each other out. So the answer is definitely not A. Let's keep red. Same with these, this is the same molecule, just almost the same molecule, just kind of one bond apart, one carbon apart. And these arrows, once again, will not cancel each other out, definitely. C also, this arrow does not get canceled out, right? There's nothing on this side to cancel that out. And so the answer is also definitely not C. However, these fluorines, look at them. The arrow points directly on opposite sides, right? They're canceling each other out. And so it's almost like this molecule does not have any polar bonds. And so this molecule definitely does not have a dipole moment, right? It's definitely nonpolar. The next problem, which molecule has a zero dipole moment? There is a typo in the version of the worksheet that I'm working on, but the worksheet that you should have been able to see on Google Drive does not have this typo. Let's take some time to actually draw out every structure so we can make sense of this. So CH3Cl, HCl, and then CH2ClF. So HCl, F, CH, Cl, 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 and then CCl4. Okay, and let's maybe look at the bonds of each of these structures. Remember that carbon-hydrogen bonds are definitely nonpolar. However, carbon-chlorine bonds are definitely polar. There's nothing on this side to cancel each other, cancel that bond out, and so this molecule is definitely going to be polar. Remember, zero dipole moment, we're looking for an answer should be overall nonpolar, right? Because it has a zero dipole moment. The next structure, although both chlorine-carbon and fluorine-carbon bonds are both nonpolar, are these arrows equal? I know I didn't draw them to scale, but think about it, right? Fluorine is much more electronegative than chlorine, and so the difference over here versus the difference over here is going to be different. Even though they're both arrows pointing in opposite directions, I didn't draw, I'm just sketching them. But are these arrows real, equal size? They're not. This arrow, if we drew it to size, should be bigger than the arrow on the left. And so this molecule, even though both arrows go in opposite directions, they don't cancel each other out. Not quite. And so this molecule, is definitely polar and does not have a zero dipole moment. The next problem, all of these carbon-chlorine bonds are going to be polar. So they're going to point away from carbon. And these two bonds do cancel each other out, right? That's great. But there's nothing going up that's going to cancel out this bond. And so this molecule overall will be still polar. The next structure, CCl4, these bonds are going to be toward chlorine in every single example. And check this out. Every single bond cancels each other out. The up and down and the left and right. And so these bonds are going to be canceling each other out. So the molecule, even though it does have polar bonds, the molecule overall is nonpolar. We're going to write nonpolar with an exclamation mark. So the answer for this problem is D. Which molecule has a zero dipole moment? We should maybe draw out, after defining this, the answer again should be nonpolar. And so A will look like this. Very similar to one of the answers in our previous problem. It has 3 lone pairs. 3 lone pairs. And carbon-fluorine bonds are definitely polar, so let's draw the arrows going this way. However, some of these bonds do cancel out, so the left and right do cancel out. But the bond looking down does not get canceled out, right? There's nothing over going the other way that would cancel it out. So A is definitely the wrong answer. We don't really have to draw a structure for B. We can kind of analyze it as it is. Right? This bond goes diagonally up and left, while this bond goes diagonally up and right. And notice that, again, I said this before, the arrows can point in any direction, diagonally left, right, up, down, it doesn't matter. We're kind of looking at them as they're drawn, right? Very literally, we're looking at these arrows very literally. And so these bonds, even they're kind of a weird direction, they're going diagonally, they still cancel each other out. Notice they're diagonally in directly opposite directions. And so I think it's B, but maybe we should examine the rest of the answers before we move on. NF3, this is an important concept. This is why the fact that nitrogen has a lone pair is so important. Nitrogen with 3 bonds is always going to look like this. We'll talk about why the structure exactly is, the reason for that, in a later video. But this nitrogen is going to look like so. And this is important to know because then you'll realize that no matter what, if nitrogen has 3 bonds, no matter what's connected to it, it's still going to be polar, right? You might think that, it could be canceled out. It cannot, right? These fluorines do cancel each other out, but there's nothing going over that cancels this fluorine out. And so this structure is still going to be polar. The next structure, check these out. Very similar bonds. Let's make sure we have it in blue just to stay consistent. These bonds are going almost in the same direction, right? There's no way that these cancel each other out. And so this molecule is still overall polar. The next structure, there was a little bit of a typo before I didn't notice, but your worksheet should be updated with this version. Let's try to draw this out. CH2, so let's make sure our colors are consistent. CH2, let's draw the H's away from each other, and the fluorine and chlorine away from each other. This is a similar example as what we did before. Make sure we draw our bonds. And chlorine, fluorine, as well as carbon, chlorine, and carbon, fluorine bonds are all definitely going to be polar. And once again, I didn't draw these arrows to scale, but the difference, this arrow should be bigger than the arrow on the right. Because the difference between fluorine and carbon is much bigger than the difference between carbon and chlorine, right? And because of that, these bonds do not cancel each other out, meaning that this structure is still overall polar. And so the answer, as we thought before, should be B. Let's do that in red. The next problem, which molecule has a dipole moment greater than 0? Well, all we're looking for in this problem is a molecule that is polar, right? We don't have to calculate any dipole moment. We're not really focusing on that in this course. We're just focusing on the fact that if it's greater than 0, the molecule must be overall polar. And so let's define every single one of our bonds in the answer choices and figure out which one of them is going to be overall polar. Carbon-fluorine bonds are definitely polar, and check it out. They kind of go in almost the same direction, meaning that they don't cancel each other out, so this one must be polar. Let's write next to it, polar. So P for polar. In this structure, well, the fluorines, carbon bonds are again polar, and they're also kind of going in the same direction. There's no way that these cancel each other out, right? Maybe rotate your head vertically to the left 90 degrees, and you'll notice that these bonds do not really cancel each other out. So once again, this structure is also polar. The third example, these carbon-fluorine bonds go away from each other, and so these two do cancel each other out. Again, like in the previous problem, they do cancel each other out, so this one is nonpolar. However, we do have an answer choice more than one of these choices, so it's going to be A and B, or both have a dipole moment greater than 0. Which molecule has a 0 dipole moment? Well, what are we looking for? We're looking for, again, a structure that is overall nonpolar. And so SO2 is going to have double bonded oxygens. It's going to be kind of bent. And check out the Vesper theory video to understand why this molecule looks like so. And the sulfur-oxygen bonds are going to be polar. Oxygen is much more electronegative than sulfur. So these are going to be pointing away from sulfur toward oxygen. And again, they're kind of diagonal, not in exactly opposite directions. And so this molecule is definitely polar. Let's write polar under it. P for polar. The next structure, CO2. Well, carbon doesn't have any lone pairs, and so these oxygens kind of are perfectly away from each other. There's no lone pairs in carbon. Check out Vesper theory, once again, to figure out why I draw the structure like so. And so these bonds are going to kind of, going to be polar. So these arrows are going to point away from carbon and toward oxygen. And notice that they do point in exactly opposite directions. They do cancel each other out. So this molecule is overall nonpolar. And I think it's B, But maybe we should check the rest of the answers to see if we're right. Ooh, I drew a polarity arrow. The next structure is CO, carbon monoxide. Carbon should have 3 bonds double bonded to oxygen, and oxygen is only left with 1 lone pair, as is carbon. And so oxygen has a formal charge of +1, while carbon has a formal charge of -1, meaning that altogether the net charge of the molecule is neutral. No matter that, oxygen is still more electronegative than carbon, and so this arrow is going to point away from carbon toward oxygen. There's definitely nothing to cancel each other out. This molecule is definitely overall polar. CHCl3, we're going to have H pointing up. Make sure the Cl's are kind of nice away from each other. And once again, carbon-chlorine bonds are polar, so they're going to point away from each other. And the left and right ones do cancel each other out, while the one going down does not have anything to cancel it out, and so it is still polar, overall polar. Let's write P under it. And so I was right. Our answer B should be the correct answer. It is the only one that is overall nonpolar. The next problem, again, which molecule has a 0 dipole moment? We should write that the answer should be nonpolar. Nonpolar. And so let's take the time to draw the Lewis structure for each of these problems. CO2, we did this in the previous example. The arrows will point away from carbon toward oxygen. They do cancel each other out. And so this molecule is nonpolar. So let's maybe draw an arrow pointing toward A to show that it is nonpolar. CH4, carbon-hydrogen bonds are not polar, and so no arrow should be drawn. Therefore, this structure is definitely overall nonpolar. My apologies. CH3, let's draw this one out. Again, carbon-hydrogen bonds as well as carbon-carbon bonds are all nonpolar. And so this structure is still overall nonpolar. So this one is also correct. And the next structure, you don't know the name of this structure, but this is benzene, right? It has a special name for it. And I'm going to redraw it, showing every single one of our carbons so we can maybe orientate ourselves a little better. Right? These are our double bonds. I know it looks a little strange, but notice that once again, every carbon-carbon bond is nonpolar. So it doesn't matter how you structure this structure, how it looks. Every bond is nonpolar, so this structure should definitely be overall nonpolar. And so the answer, all of these choices, makes sense. The next problem, which molecule has a dipole moment greater than 0? We're looking for an answer that is overall polar. And the first answer, notice that this beryllium chloride, dichlorine, or whatever it's called, should be, like, it doesn't even matter because this is an ionic bond, right? Beryllium is a metal. Chlorine is a nonmetal. And so this answer overall is polar, right? No matter what, it's ionic. So it has nothing to do with our answers at all. Boron chlorine, boron trichloride. Notice that unlike nitrogen, right, boron forms 3 bonds but has no lone pairs. And so each of these answers, right, each of these bonds should be polar, pointing away from boron and toward chlorine. And notice that I like to imagine that these 2 bonds kind of combine into one, right? They're almost like going away from each other in opposite directions, but it's almost like they combine into one equal vector right in the middle of them. And this vector completely cancels out the vector going opposite. And so this structure is overall polar, nonpolar. Let's use red. CO2, carbon dioxide. We drew this a couple times already. The arrows go away from carbon toward oxygen. And so these 2 vectors do cancel each other out. And so this structure is overall nonpolar. H2O, we're going to have hydrogens away from oxygen. Structure looks like this. We drew this before, actually in the topic video. And oxygen is more electronegative than hydrogen, meaning that the arrows point away from hydrogen toward oxygen. And these arrows do not cancel each other out, meaning that this is probably polar. So I think it might be this answer. But let's do the next E, the next choice just to make sure. So CCl4 is going to look like this. And each of these bonds, right, chlorine is definitely more electronegative than carbon. So each of these bonds does cancel out. Right? Up and down cancel each other out, and left and right cancel each other out. And so this structure is still overall nonpolar. So I was correct. The answer should be D. Which molecule has a dipole moment greater than 0? We're looking for an answer that is overall polar. So let's take the time to draw each of these structures. SO2 looks like this, with 2 lone pairs, kind of like O2 almost. And so oxygen is more electronegative than sulfur, meaning that these arrows point away from sulfur, and these do not cancel each other out. So this structure is polar. So I think it might be A, but let's do the rest just to make sure. CO2, we drew it in the last problem. We'll draw it again. These bonds go away from carbon toward oxygen, and they cancel each other out, meaning that this structure is definitely nonpolar. So we can eliminate CO2. CCl4, so draw this again. These bonds all go away from carbon toward chlorine. And so these left and right do cancel each other out. Up and down do cancel each other out. And so this molecule is still overall nonpolar. BF3, we did a similar one in the previous problem. Boron forms 3 bonds and does not have any lone pairs. Fluorine is more electronegative than boron. And so notice that these 2 vectors kind of combine into one big one, right? Right in the middle of them. And then that vector that we combined is directly opposite from the vector going down. And so BF3 will still be nonpolar. The next structure, all these carbon-chlorine bonds are polar. So let's draw the arrows to show that. And notice that, again, it's kind of in a weird direction, but they still do cancel each other out. Right? This one cancels out this one, and the one on the left cancels out this one. And so this structure is still overall nonpolar, meaning that their answer was A. Which molecule has a 0 dipole moment? We're looking for an answer that is overall nonpolar. And so this, let's evaluate each of these bonds. Every carbon-chlorine bond is polar. So let's draw something like this. Like this. And let's look at each answer choice one by one. A, this bond has nothing on the other side to cancel each other out. And so this answer is definitely wrong. These 2 answers have nothing, they don't really get canceled out either. They're kind of looking in almost the same direction. So B is also wrong. Answer C, notice that these bonds are kind of looking in opposite directions. And so they do cancel each other out. So I think it might be C, but let's check D just to make sure. In D, notice that again, like in the previous problems, these bonds do cancel each other out, but there's no bond in the opposite bottom left corner to cancel out this chlorine, right? And so this bond, this structure should still be overall polar. So the answer is C. Which of the following molecules or ions contain polar bonds? It's possible. I think this answer might have multiple choices, multiple answers, but let's draw each of the structures. O3, ozone, should look like this. Like this. Drew an extra bond in there. And this middle oxygen is positively charged, while the oxygen on the left is negatively charged. And each of these bonds, oxygen-oxygen bonds, are all nonpolar. And none of these bonds are actually polar. So we can eliminate A, right? Ozone does not have any polar bonds. O2, let's take the time to draw oxygen gas. This is how oxygen appears as a gaseous form, as O2. Notice that again, oxygen-oxygen bonds are not polar. And so this structure does not have any polar bonds. NO3 will look like this. The structure on this oxygen is definitely neutral, while the ones with single bonds are both going to be negative. And nitrogen ends up positively charged. So the overall charge of this is -1, which makes sense. And each of these bonds is actually polar. Oxygen-nitrogen bonds are definitely polar. And so this is one of the correct answer choices. It's good. CO2. We've drawn this many times, this worksheet. Each of these bonds is actually polar. And so D is also an answer. H2S is going to look like this. H, two lone pairs. And both of the hydrogen-sulfur bonds are polar, going towards sulfur. And so H2S is also an answer. So make sure the color is the same. BH4. Let's draw this one out. Has a negative formal charge because the boron is, has an extra bond in there. And so each of these bonds, hydrogen-boron bonds, are definitely still polar. Structure is overall nonpolar, but we still do have polar bonds. So this answer does make sense. S8, I'm not even going to try to draw the structure out. SS, no matter how we organize them, sulfur-sulfur bonds are nonpolar. And so this structure is definitely overall nonpolar, but it does not have any polar bonds. Using the Lewis structure, determine if the following molecules have a dipole moment. Phosphorus 5 is going to look like a little star, with phosphorus all around. And let's take the time to make sure our Lewis structure is correct. Three lone pairs on each of the fluorines. And each phosphorus-fluorine bond is polar. So let's draw arrows pointing toward fluorine. Let's use blue to show that it is polar. And notice that, once again, the ones going left and right definitely cancel each other out. But you would think that, oh, these don't cancel each other out. But these bonds, these ones going diagonally left and right, kind of can combine into a bigger vector going fully down, right? They're almost like combining into each other. This makes more sense if you took physics. And so these vectors end up both looking up and down, meaning that this structure is overall nonpolar. Draw it in black. Overall nonpolar, meaning no dipole moment. No dipole moment. CS2. This carbon is going to be in the middle with double bonds to sulfur, and then two lone pairs. And carbon-sulfur bonds are definitely polar, with the arrow pointing towards sulfur. And so notice that these bonds do cancel each other out. Even though they're polar, the structure is still overall nonpolar, which means that it has no dipole moment. BrO3, the structure is a little bit different. It's kind of an exception. We have a lot of these examples in which the halogens will form more than one bond. It's possible. So we'll have a double bonded to oxygen, up and down. And oxygen will end up having three lone pairs with a negative charge, while these ones just have a single lone pair, and bromine does still have a lone pair in there. And each of these bonds is polar, going toward bromine. Bromine is more electronegative. It's right under almost right under fluorine. And so these structures, notice that the arrows pointing up and down do cancel each other out, but there's nothing on the left side to cancel out that bond on the right. And so this structure is overall polar, which means it does have a dipole moment. NH4, ammonium, is going to look like this. We drew the structure in one of my earliest videos. Actually, the structure on formal charge. Nitrogen-hydrogen bonds are definitely polar. They're all going to point toward nitrogen. And notice that they all cancel out, right? The one left and right cancels each other out, and the one up and down cancel each other out. So this structure is overall polar. Oh, oops. This structure is overall nonpolar. So therefore it has no dipole moment. No dipole moment. SCl4, the structure is going to look like this. Remember, sulfur 6, so it's going to have, let me make sure to draw it in red. It's going to have 4 bonds of chlorine, kind of looking outwards. and it's still going to have a lone pair. So sulfur and chlorine are polar bonds looking toward chlorine. And notice that the ones left and right do cancel each other out, but the ones going up, diagonally left and diagonally right, do not cancel each other out. And so this structure is going to be overall polar, meaning that it does have a dipole moment. And this is, I know my handwriting isn't too great in this, while I'm trying to do this explainer video, but in the answer key, it's definitely a lot better. Bromine pentafluoride, I think is the name, is going to be looking like this. Kind of like a star, almost like sulfur, with a lone pair. And fluorine, each fluorine also has a lone pair. And each bromine-fluorine bond is polar, looking toward fluorine. And they do cancel each other out. Each bond cancels each other out on the left and right, but the ones going up diagonally left and diagonally right don't, right? They don't get canceled out. And so this structure is still overall polar, and it does have a dipole moment. BF3, again, boron forms 3 bonds but does not have a lone pair. And so this is really important to memorize, almost memorize it, right? I remember that boron forms 3 bonds with no lone pair. Kind of looks like nitrogen, but almost like nitrogen's little brother. And so each of these bonds is going to be polar toward fluorine. And you would think, oh, there's no cancellation, but these two looking down kind of cancel out and make just an equal bond looking down. And these two vectors do cancel each other out. So the structure is overall nonpolar. And it has no dipole moment. SCl6, a little bit of a complicated structure. We're going to have chlorine looking up, chlorine looking down, and diagonally left, in all directions diagonally. And sulfur ends up having 0 lone pairs. And so let's specify each of the lone pairs on chlorine. It takes time to draw these little dots. It's a little uncomfortable on a writing tablet too. And so each of these bonds is still going to be polar toward chlorine. So let's specify the arrows. And let's take these vectors very literally to cancel each other out. The top and bottom cancel each other out. And then this one diagonally right and up cancels out the one diagonally left and down. And the one diagonally left and up cancels the one diagonally right and down. And so this structure is overall nonpolar. So it has no dipole moment. The next structure, pH3, will look like this. And each polar phosphorus hydrogen bond is polar toward phosphorus. Notice that the ones left and right do cancel each other out, but the one up and down do not. And so this structure is overall polar, meaning that it does have a dipole moment. NF3, again, it has 3 bonds and a lone pair. Notice that each of these bonds are polar toward fluorine. Make sure we use the right color. And the ones left and right do cancel each other out, but the one going up, there's nothing to cancel that one out. And so this structure is overall polar, and it does have a dipole moment. SO4 is going to look like this. Make it look neat with both of the double bonds up and down and the single bonds left and right. So this is going to be like this. Right? Sulfur and oxygen bonds are all polar toward oxygen. Let's draw the arrow specifying that. And notice that all the arrows cancel each other out. Right? Up and down cancel each other out. Left and right cancel each other out. Meaning that this structure is nonpolar. And it has no dipole moment. The next problem, CO3, is going to look like this, with a double bond looking up, or it doesn't matter what direction you draw it in, but it does have two negatively charged oxygens. One bond, three lone pairs. The oxygen up does not have a formal charge. And we're going to draw arrows away from carbon toward oxygen, because oxygen is more electronegative. And these bonds going diagonally down do cancel each other out into one bigger bond looking directly in between them. And then it turns out that these bonds do cancel each other out, meaning that CO3 is overall nonpolar. Let's make that in black. Nonpolar. Meaning that it has no dipole moment. SiCl4 is going to look like this. Chlorine each has a 3 lone pairs. And the bonds, carbon bond, chlorine bonds are polar, looking toward chlorine. So let's draw the arrows to prove that. And they do cancel each other out. So the left and right ones do cancel each other out, and the one up and down do cancel each other out. So this structure is overall nonpolar, meaning that it has no dipole moment. ClO3, kind of an exception to the halogen rule. Chlorine is in the center, surrounded by oxygens. So two double bonded oxygens, chlorine has a lone pair, and one of the oxygens has a negative charge. So once we draw this, let's draw the vectors to show polarity of the bonds. The ones up and down do cancel each other out. The one going right has nothing on the left side to cancel each other out. Cancel that one out. And so this structure is overall polar, meaning that it does have a dipole moment. CH2O is going to look like this. And there is a polarity between carbon and oxygen. There's no polarity between carbon and hydrogen, meaning that this structure, there's nothing to cancel out this arrow going down, going up. And so the structure is overall polar, meaning that it does have a dipole moment. NO3 should look like this. It does not have any lone pairs because it has 4 bonds and 2 negatively charged oxygens, 3 lone pairs. In the center, nitrogen does have a positive formal charge. The lone pairs around the oxygen, there's 2 lone pairs around the oxygen going up. And each of the oxygen-nitrogen bonds are polar, with arrows pointing toward oxygen. And notice that these two arrows combine into an arrow going down. And then that turns out that these 2 arrows do cancel each other out, meaning that this structure is overall nonpolar with no dipole moment. The next structure, ozone, O3, we drew it earlier in this worksheet, should look like this. And it doesn't even matter how we draw this structure because oxygen-oxygen bonds are all nonpolar, right? Even though we do have some charges, let's specify those. Every oxygen-oxygen bond is nonpolar. So it doesn't even matter, we don't draw any arrows. This structure is overall nonpolar, meaning that it has no dipole moment. CCl4 should look like this. We drew the structure a couple times this worksheet. And every chlorine has 3 lone pairs. And each carbon-chlorine bond is polar, going toward chlorine. And they do all cancel each other out. The left and right cancel each other out, and the up and down cancel each other out, meaning that the structure is overall nonpolar with no dipole moment. AlH3 kind of looks like boron, 3 bonds, no lone pairs. And so should look something like this, almost fully symmetrical. Aluminum hydrogen bonds are polar toward aluminum. Oh, that one's wrong direction. And notice that again, these vectors going diagonally do cancel out into a different vector right in between them, going toward aluminum. And then the ones up and down end up canceling each other out to prove that aluminum, AlH3, is nonpolar with no dipole moment. SO2, drew the structure a couple times. 2 double bonded oxygens and 2 lone pairs on the sulfur, 2 lone pairs on the oxygens. The sulfur-oxygen bonds are polar, going toward oxygen. Notice that these bonds do not cancel each other out. This structure is overall polar with a dipole moment. SO3 will look like this. 3 double bonded oxygens, and there's no lone pairs in the sulfur. There are still lone pairs in the oxygens. And every sulfur-oxygen bond is polar, meaning that looks like this. And again, these bonds looking diagonally do cancel each other out to form a different bond looking directly down. And then the ones up and down do cancel each other out, meaning that this structure is overall nonpolar with no dipole moment. Carbon monoxide will look like this. Triple bonded oxygen, triple bonded carbon, which means that the oxygen is positively charged while the carbon is negatively charged. And this bond, the carbon-oxygen bond, is again nonpolar, going toward oxygen, and so this structure is still overall polar. There's nothing to cancel out that bond, meaning that it does have a dipole moment. CHCl3 looks like this, with carbon-chlorine bonds are polar, and so they do cancel each other out. 2 of them. The ones looking up and down, nothing to cancel out this one looking down, and so this structure is overall polar, and it does have a dipole moment. BRF3, bromine with fluorine, and bromine has a lone pair. Each fluorine has 3 lone pairs, and each of these valence electron, each of these bonds, fluorine is definitely more electronegative than bromine, so the bonds looking up and down do cancel each other out, but there's nothing on the left side to cancel out that bromine on the right, and so this structure is overall polar, meaning it does have a dipole moment. H2S is going to look like this, with 2 lone pairs on the sulfur, no lone pairs on the hydrogens, and each of the hydrogen-sulfur bonds are polar, going towards sulfur, and they don't cancel each other out, meaning that this structure is overall polar with no dipole moment. I3, we don't even really have to draw this structure, but if we do, it ends up looking like this. Each of the iodines on the left and right sides have 3 lone pairs, and the iodine in the middle, again, has 3 lone pairs but a negative charge. And every iodine-iodine bond is nonpolar, meaning that the entire structure is still nonpolar with no dipole moment. This concludes the entire polarity and partial charges worksheet. If you didn't get a chance to do this or want to check out the answer key again, it's in the description below. And if you're confused with this topic, check out the topic video, again, also in the description below. And I'll see you guys in the next one.